Nitrocellulose and PVDF are the most popular and suitable microporous membranes for the Western blot application. The choice is defined by the parameters of your experiment, which include the size of your target protein, binding capacity of the membrane, requirements for sensitivity, and if stripping and reprobing is needed. Membranes have three-dimensional structure, which is very similar to a sponge with pores. The pores provide internal surface area for protein binding that is much higher than just the frontal surface area of the membrane. Very little protein binds to the surface compared to the amount of protein binding throughout the porous network. The pore size, typically 0.45 and 0.22 micron for immunodetection membranes, is derived from the original usage of membranes for filtration. The size indicated determines the smallest diameter of protein that is retained by a membrane in that context. Pore size actually describes the amount of inner surface area of the membrane. For example, a 0.45 PVDF membrane has an internal surface area of approximately 400 centimeters squared internal surface area per centimeter squared frontal surface area, and combined approximately 130 micrograms of BSA per centimeter squared. A 0.22 micron PVDF membrane has approximately 2,000 centimeters squared internal surface area per centimeter squared frontal surface area and binds about 400 micrograms of BSA per centimeter squared. The discrepancy between the amount of surface area available for binding and the amount of protein that actually does bind is probably due to steric hindrance of actual proteins versus the gas analysis method that's used to determine the surface area. It is important to note that higher binding capacity membranes do not always equate to higher sensitivity. The smaller pore size of a 0.22 micron membrane can give rise to inefficient blocking and steric hindrance, which can prevent antibodies from reaching their target antigen. However, the 0.22 micron membranes have been quite useful for retention of higher amounts of small proteins. Let's take a look at each membrane individually. Nitrocellulose is easily hydrated and naturally exhibits very low background. Proteins are thought to bind mostly by hydrophobic interactions in a nearly instantaneous fashion. Yet, this desirable characteristic also makes it difficult to effectively strip without using very stringent conditions. Nitrocellulose is well known for its poor chemical resistance to solvents and harsh conditions, which make it weak and fragile. Supported nitrocellulose has much better mechanical strength than pure cast nitrocellulose and is the more durable choice. PVDF has improved mechanical strength and better chemical resistance than nitrocellulose, which makes it a better choice of membrane if you want to strip and reprobe your blot. Protein binding is thought to occur through hydrophobic and dipole interactions. PVDF cannot be manufactured with surfactants, which creates the primary disadvantage of PVDF. It is very hydrophobic and must be wet first with methanol, ethanol, or isopropanol, adding a step to the process. If not done properly, an incompletely wet membrane can compromise the Western blot. PVDF also exhibits higher background when using fluorescent-based detection methods.